Hi, AP Chem. Yesterday we were introduced to equilibrium and the concepts surrounding equilibrium. And we ended yesterday by talking about the law of mass action, or the equilibrium constant, K. So today I want to work with K a little bit. Now, when we are in person and we do a little bit of practice together, we're going to kind of look at K from a couple different angles. What does it look like for a forward reaction? Does it look the same or different for a backwards reaction? What if we multiply the reaction? So we're going to manipulate K and look at it a little bit to better understand K and do a little bit of this practice together. But in general, for K, just know that it's like any other model that we come across in chemistry. It's a model. It's used to explain what we see happening. It's used to predict what is going to happen. But it's not a perfect model. Just like all of our models break down at some point in time, the law of mass action is also a flawed model. But it's close enough to what actually occurs to be really useful. It's usefully accurate. So much so that in industries, when compounds are being tried, when industries are trying to produce compounds, they look to the law of mass action to kind of figure out what their reaction is going to look like and how they can manipulate it to look a little bit more favorable for them. One of the big ideas that you have to keep in mind when doing the law of mass action is at the bottom, that K, no matter what you start with, when your system hits equilibrium K, the equilibrium constant will always be the same. Concentrations or equilibrium positions of your reactants and products will not. K will be the same. Concentrations will not. The concentrations can ebb and flow as long as they always agree with that specific ratio between the products and the reactants. Said another way, at any given temperature, there's going to be one equilibrium constant, but an infinite amount of equilibrium positions, right? So it's really easy to get kind of lost in this math, right? There's going to be so many numbers, there's going to be equations, and we're trying to manipulate it all and keep track of it all. It's really easy to get buried in the math and just see the numbers and not really understand what's going on in the big picture. So keep this in mind. This is your big picture view as we kind of get into the math a little bit farther. Okay, so for example, just to illustrate this point to you, I want to do a little calculation here. So this data that you see in front of you is from a specific reaction. So both reactions are going to happen at 600 degrees Celsius, and it's a reaction between gaseous sulfur dioxide and oxygen to form gaseous sulfur trioxide, okay? And you can see the results. Here's experiment 1 to the left. Here's experiment 2 to the right. They give you the positions that all of these things were at initially, and then they give you the positions at equilibrium. Again, for experiment 2, here's initial positions, and here's positions at equilibrium. So if we look at these, first of all, I want you to look at the initial concentrations and see if you can notice similarities and differences. While you do that, I'm going to write out this reaction. All right, so you can see in experiment 1, they started with a little bit of everything, and in experiment 2, they were completely missing oxygen. Oxygen wasn't there. And so experiment 1 tended to lose reactants. Notice reactants in experiment 1 started high and then got a little bit lower. The product started low and got a little bit higher. Experiment 2 went a totally different direction. The reactants actually increased. Notice you had some sulfur dioxide present initially and no oxygen, and both of those amounts actually increased. The products actually decreased a little bit in order to get to equilibrium. So they started in different places, they shuffled to different places, and then notice our equilibrium positions. Our equilibrium positions for experiment 1 and experiment 2 don't look anything alike. They're at completely different experimental positions, right? Equilibrium positions. The thing we want to verify now is that their Ks are the same. So here we have a balanced reaction between sulfur dioxide and oxygen going to sulfur trioxide. Let's just double check this. 2 sulfurs, and then 4 plus 2 is 6 oxygens. 2 times 3 is 6 oxygens. Okay, so there's our balanced formula. The first thing I want you to do is just write a generalized K equation. So pause here and do that. All right, so that's what our K equation should look like. And now let's take these equilibrium positions and plug them into our K equation and see, do we actually get the same K for both experiments? We have the same reaction, we have the same temperature. Theoretically, we should come out with the same equilibrium constant, right? Let's see if we actually do or not. So again, feel free to pause the video here and see if you can beat me to this answer and get a similar answer than I do. Okay, I got 4.36 on the first one. Let's see what I get on the second one. All right, in the first experiment, I got 4.36 as my K. And in the second experiment, I got 4.32 as my K. So again, They're not exactly the same. I mean, they do break down when it gets to the 100th of a degree. But they are really close. 4.3, 4.3. No matter what the equilibrium positions are, the equilibrium positions can change. The equilibrium constant will not. The equilibrium constant will be the same as long as the reaction and the temperature are the same. Equilibrium positions can change. Equilibrium constant will not. Okay, there we go. So there's evidence for our big picture idea. Now let's get into some of the details about this law of mass action. So first of all, the law of mass action that we are dealing with is in terms of concentration. Every K that we have written so far has been K in terms of concentration. You can see here's my K, here's my K equation. This is written for a specific reaction. Let's see, it's got to be N2 plus 3H2 goes to NH3. And there's two of those. So does that check out? Yes, that checks out. All right, so there's my K equation for the specific reaction. Notice it is in terms of concentration. This bracket means concentration, right? So what we're really dealing with is K in terms of concentration. But sometimes concentration is not the easiest thing to deal with. If we're dealing with an aqueous solution, certainly it is. We're going to deal with molarity. It's really practical to deal with molarity. We're going to deal with K in terms of molarity, right? But if we're dealing with gases, reactions can happen in the gas phase as well. In fact, our example on the last slide was an example that happened in terms of the gas phase, right? And so when we're dealing with gases, it's not as convenient to measure gases in terms of concentration. Usually what we do when we measure gases or the percentage of a specific gas inside the total is we measure stuff in terms of partial pressure, right? When we're talking about the percentage of the total pressure that is dedicated to a specific gas, what we come out with is partial pressure. Our percentage is just a percentage in terms of moles because we're chemists, and it's a lot easier to deal with percentages in terms of moles. So rather than having to calculate from partial pressure into concentration in order to deal with K, we can deal with K just in terms of partial pressure by themselves. Now, partial pressure and concentration are related, and you can see that worked out a little bit at the top of this page. But let me show you that relationship. So if we take the ideal gas law, PV equals nRT, right? And we want to rearrange this in terms of concentration. So what is concentration? If I look at the concentration of N2 over here, what do I mean by concentration? I mean molarity, right? So what are the units of molarity? Units of molarity are moles per liter. So can we rearrange the ideal gas law in order to have concentration in terms of molarity? Yeah, sure we can. So now would be a good time. Practice your algebra skills here. See if you can rearrange the ideal gas law so that everything's on one side and molarity is on the other side. All right, there we go. So we have the ideal gas law arranged in terms of molarity right here. Now, notice that they used a C for concentration. So we can substitute in a C in place of this N over V. And that's what they have not shown very well, but C equals P over RT. If you see this expression, that's what they mean by this expression. It's just the ideal gas law solved for concentration, right? So concentration and partial pressure are related. They're related through the ideal gas law. So we can deal with K in terms of concentration. We can also deal with K in terms of partial pressure. So we would call K, when we are substituting in the values for partial pressure, we would call it Kp. And this is what it would look like. It would be the exact same equation, only instead of using concentration for everything, you'd use partial pressure for everything. But other than that, it's still the same. Products on the top, reactants on the bottom, everything is raised to its coefficient. So, take away from this slide, concentration and partial pressure are related. They're related through the ideal gas law. Therefore, we can write our equilibrium constant in terms of concentration, or we can write the ideal or the equilibrium constant in terms of partial pressure. So let's take a look at using this. Okay, for example, here we go. Formation of nitrosyl chloride was studied at 25 degrees Celsius. The pressures at equilibrium were found to be here below. So calculate the value of Kp for this reaction. This would be a good place to pause the video and see if you can work ahead and beat me to the answer. So I'm going to start by writing my K equation, NaCl squared over NO squared Cl2 raised to the first. And now I'm going to plug in my values. 1.2 atmospheres squared over 5 times 10 to the negative second squared, 3 times 10 to the negative first to the first. Okay, now I wrote my K equation in terms of concentration, but I plugged it in terms of pressure. And so I'm going to readjust here. And instead of writing it in terms of concentration, let's write it in terms of pressures. So I want the partial pressure of NaCl squared. I want the partial pressure of NO also squared. And then I want the partial pressure of Cl2 raised to the first. Okay, so now I have plugged in my partial pressure values and I can calculate it out and answer. All right, and the Kp I get is 1920. I'm just going to double check my sig figs. My sig figs are in terms of 2, so I'm going to write 1.9 times 10 to the third is equal to my Kp. There we go. So did you get something similar? And do you have any questions on that? Notice it's really similar, right? We did this same idea in terms of concentration. We can just do it in pressure. The only thing that changes is the units. And this leads us to ask the question, are K in terms of concentration and K in terms of pressure going to be the same? Now, the equation looks very similar, right? We set the equation up the same way, but the values, since we're substituting in numbers with different units, the values of K in terms of C and K in terms of P are going to be different. But like we saw with the ideal gas law, they're related, right? So if we're given one, is there a set relationship so that we can calculate the other? Well, let's take a look at that. Okay, so here they again give us the same expression of K in terms of concentration, and we already looked at how the ideal gas law can be rearranged in order to show us that relationship between concentration and pressure. And we're still dealing with the same reaction, nitrogen reacting with hydrogen gas, giving us ammonia. All right. So what we want to do is we want to see if we can substitute in this equation that we solved for, this relationship we solved for using the ideal gas law. If we can substitute that in, eliminate the concentrations, and solve for pressures. So let's try and do that. We know we have concentrations already. Let's substitute in those concentrations for the other half of that reaction, shall we? Let me erase this so you can see very clearly what that relationship is that we solve for. Okay, so all I'm going to do is I'm going to take that K equation, and instead of having concentration of ammonia, I'm going to have partial pressure of ammonia over RT. But I'm going to keep the rest of the equation the same. So concentration is squared. I'm going to keep this partial pressure term squared as well. Same for nitrogen. Raised to the first. Same for hydrogen. Raised to the third. Again, we are looking for that relationship between K in terms of concentration and K in terms of pressure. We're trying to derive a set relationship so that if we're given one K, we can solve for the other K. All right, so now that we have substituted in this relationship for concentration, now let's simplify this. I want you to pause the video here and see if you can simplify this relationship. Pull out all the constants, group them together, pull out anything that's going to vary between all your equilibrium positions, put them together, and go. So all I've done is I've pulled out partial pressures because those are going to be the equilibrium positions that vary depending on what my initial concentrations are, right? And I pulled out everything else that's a constant, the RTs, and put them over to the side. I'm going to simplify this a little bit more. Okay, so there's our relationship way down at the bottom. Noticed all I did from separating the partial pressures and the constants, then I took all the constants and just put them all together, right? And then because I ended up with a negative exponent, so multiplying by a fraction is the same as dividing by its inverse, right? So I just flipped the fraction and then made the exponent positive. So there's a relationship. There is definitely a relationship between K in terms of concentrations and K in terms of partial pressures. Now here's my next question to you. Will this relationship always be the same? If I give you a different reaction, let's say I give you a reaction of hydrogen reacting with oxygen to form water. And let's go ahead and balance it. Okay, different reaction. I'm going to have a different law of mass action, right? My law of mass action is going to look like H2O squared over H2 squared times O2. Okay, so different reaction, different K expression. Will the relationship between Kc and Kp be exactly the same? Could I take Kc and set it up to be equal to the partial pressure of everything? Well, let's just write Kp, right? That's this term right here, K in terms of P, times RT to the second. Could I do that? What do you think? And hopefully you realize that that would not actually be the expression. That's the relationship for the last reaction we're looking at. That's not the relationship for this reaction. What would be different? The amount of RTs, right? This expression right here, even if we just group this all together and call it Kp, okay, that's a hunky-dory way to do that. Okay, this expression over here of all the RTs is very dependent on the exponents, right? And where did these exponents come from? They came from the equation. So this exponent portion of the RT is going to be dependent on the coefficients in your reaction. So can we write that instead of giving it a specific number like we did in the last example? Can we turn that into variables? What would that look like if they were variables? And notice here that 2 that came out, RT raised to the 2, right? It came from taking our reactants, 1 and 3, and subtracting the coefficients of our products, which was a 2. So coefficients of our reactants minus the coefficients of our products, that's what actually got us to the 2. So 3 plus 1 minus 2 equals 2, right? So we can use that in place of a number. Reactants minus products. So there you go. We now have a relationship between Kc and Kp that we can substitute in for any equation we come to. Kc is going to be equal to Kp times RT raised to coefficients of reactants minus coefficients of products. Woo, it doesn't feel good to derive something yourself, to come up with that relationship yourself. Feels so good. In the middle of the test, when you're panicking and your mind just goes blank, you can think, I can derive stuff. And then you can go do it. And actually, I would check your reference sheet. Perhaps you don't actually have to derive this in the middle of the test, perhaps you can go check your reference sheet. This may be on it. Definitely worth checking. If it's not on it, I would add it to that last sheet in your notebook, the sheet of things to review right before the test, right? And maybe remind yourself of how we got the R minus P, why it is reactants minus products. Okay, now that we have a relationship, we can use it. Here we go. Using the value of Kp from 2 slides back, 1.9 times 10 to the third, calculate K at 25 degrees Celsius, so the same temperature, for the reaction, right? So they gave us the same reaction, they gave us our Kp, they gave us the same temperature. They didn't change anything, but instead of wanting Kp, now they just want K. So notice, before we even begin this, if they list K, they just say, write the K, write the equilibrium constant. They are referring to the one in terms of concentration. Kc is kind of your default. So if they don't specify which one they want the one in terms of concentration. All right, this would be a good example to try your hand at, and when we come back together, we'll do this one together as well. Can you calculate between the two now that we have the relationship? Okay, heterogeneous equilibria. So big words, let's break that down. So heterogeneous means not the same, right? Something that's hetero means you have different parts. Well, that's what's happening in this equilibria expression as well. Notice, here's our example reaction of a heterogeneous equilibria, and the things that's different between the reactants and all the products are the phases. So a heterogeneous equilibria refers, there's the word, to an equilibria situation, a reaction that's gone to equilibrium, where the species involved are at different phases. So if you actually go back in our slides, you can double check this. All of the ones we've been dealing with so far, they're either all aqueous or they're all gaseous. Well, here we have one in front of us where some of them are solid, some of them are gas. So how do we deal with this? Okay, before we kind of talk through that, let's just write the K, right? This is another good thing. If you run across an equilibria expression and your mind kind of goes blank in the middle of the test, you know what you can do? You can write the K. That's probably where you have to start anyway. So let's just take a minute and write the K expression for this. All right, here we go. There's my K expression. Okay, so now that we have written this, let's talk about what they actually mean. When we have a gas, like CO2, we can talk about the percentage of the total gas that's present, right? We can talk about the percentage of the total gas that is due to carbon dioxide. That's going to be called the partial pressure of carbon dioxide, right? It's a part out of a whole. Okay, we can do the same thing for aqueous solutions. If we're talking about aqueous solutions, we can talk about concentration. Concentration is a part out of a whole. The part is the moles, the whole is the liters, right? How many moles in these liters total? We can talk about the part out of the whole. Well, for solids, we can't really talk about a part out of a whole. And it's really the same thing for liquids as well. If I have a pure solid, right, what is my part versus the whole? Well, we can talk about like molecules versus space, perhaps. But other than that, usually when we talk about an atom or we talk about a crystal and we talk about like the volume of it or the density of it, we would look at the space in between. If we're not talking about those things, we kind of assume that all the space is just evenly distributed between the atoms. And we say that it's pure, right? It's the only thing present. So it's the whole thing out of the whole thing, right? If you have a pie, for example, that has crust and cherries, well, you can talk about what percentage of the pie would be cherries, right? Cherries over the whole pie. But if you have a pie that's just all whipped cream, if you want to talk about percentage, you're talking about the whipped cream out of the whipped cream, right? There is no part. It's already equal to 1. And that's what's happening if you have a pure substance present. If you have a pure substance present, you have the whole thing present in front of you. And so the concentration really is equal to 1. It's the whole thing. It's the whole shebang. It's 100%. Your fraction is now 1. And so if we look at that in terms of our K equation, if we look at our solids and we consider them to be at 100%, the fraction for these solids actually becomes a 1. And so our equilibrium constant really is only dependent on those things that can fluctuate in percentages, those gases and those aqueous substances. So when we look at K and when we write the K equation, the only phases we are going to include in that equilibrium constant or that law of mass action are gases and or aqueous substances. We're not going to include solids. We're not going to include pure solids. We're not going to include pure liquids because their concentration is already 100%. Okay, so takeaway from this, only include gases and aqueous solutions in your K equation. Okay, for example, let's write the K equation for these. On the first one, let's write K in terms of concentration. On the second one, let's write K in terms, I guess we're repeating it. Let's just do both of them. Well, since we're dealing with gases, I guess we'll do K in terms of pressure. Okay, write the Kp for both of these, please. Now would be a good time to pause it and see if you can beat me there. Okay, so as you can see, just by changing phase, notice the reactions are exactly the same. The only difference is the phase of the water, right? And just by changing a phase, you're going to change the K equation. So phase matters. Pay attention to it. All right, here's a couple examples we can go through together in class. All right, and we get to this third section of our chapter, application of K. So we're going to turn the corner here into talking about K and what K is and what equilibrium is, and trying to wrap our brain around these concepts to applying these concepts. So we're going to go away from concepts into math, basically. All right, so what do we use K for? We use it for a couple different things. First of all, it can predict the tendency of a reaction to occur or not occur. Now remember, this is separate. This is not talking about how fast the reaction will occur. It's just talking about if it will occur. right? So again, we want to make this distinction. This is not speaking to the kinetics of a reaction. Second of all, we can use it to predict if our system is at equilibrium already. If I'm given a set of positions or concentrations of my reactants and products, I can look at that set of positions and determine, am I at equilibrium or not? And then the third thing I can actually use K to predict is, if I'm not at equilibrium, which direction will it go in order to reach equilibrium? Will the reaction go forward to get to equilibrium, or will the reaction go backwards? So we want to look at applying some numbers here to some specific situations in order to draw these three conclusions. Now, before we get into numbers, we're going to ease you into this idea by using symbols. Okay, so for example, I have a reaction. Here's my reaction, and it's written in terms of symbols. So notice the little blue symbols and little red symbols, they represent two different types of atoms, and they give you a K for this equation. So if we wanted to write this in symbols, we could write like A to the third plus AB goes to A to the second plus A squared, A to the second B, something like that. Okay, so notice we have two different types of atoms involved in here, and this is kind of what it would look like. Okay, so if we're going to write the equilibrium constant, let's do that. The expression for K is equal to 16, which is equal to blue, blue plus blue, red, blue. Oh no, not plus. Times over my reactants. Blue, 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 reddish pink. There we go. There's my K equation. Okay, so I'm given this experiment here. I have my initial amounts. So welcome back to ice charts. Okay, this is when ice charts become really important to you. Now, before we move forward, let me get on my soapbox here a little bit and talk about ice charts. You don't have to use them. If you hate ice charts, you can do all of this math without using the ice chart. The problem is you have a lot of different stuff to keep track of, right? If you're going to talk about change for 4 different molecules, you're going to have to do the stoichiometry for each of those 4 different molecules separately, right? And at the same time, you want to keep track of how the stoichiometry for those 4 different molecules are related to each other. So that's what a chart does for you. Notice you have 4 different stoichiometric equations here. Each column is keeping track of the stoichiometry for that specific molecule. And at the same time, because we do it in a table, you can see how they're related to each other, right? How are all the initial amounts related? How is the change related to each other? That's a huge one. And then how are the equilibrium positions equal to each other? And then when you're done, it's still in a neat little table. So if you want all the equilibrium positions, you can go ahead and take all of them instead of searching all over your paper to see where you happen to put them. If you want all your initial concentrations, you have them right there in a row, right? You don't have to search all over your paper to figure out where you did these calculations. So the benefit of the ice chart is organization and comparison, right? So I highly encourage you to try to use ice charts as we move forward. If you're really against it, you can knock your socks off and just use stoichiometry. All right, so here we go. Notice that in this ice chart, they give us an initial amount and they give us a change. Now, they're not telling you if that change is going to lead to equilibrium or not. Notice they use an F meaning final, meaning we don't really know if we're at equilibrium or not yet. So let's go through, use the change they've given us, and figure out where we would be at if this reaction proceeded forward. So now would be a good time to pause the video, see if you can fill out this chart on your own, and see if you get the same final amounts as I do. Okay, so reactants are going to, we're going to use reactants. They tell you right here we're going to use reactants. And if we're using reactants, that means we're making products. Okay, so now I can calculate 9 minus 5, my final amount. 12 minus 5, 0 plus 5, 0 plus 5. Okay, I have my final amounts of each. Check. What unit are we working in? Probably molarity, hopefully, because our K is in terms of concentration. Is this system at equilibrium? Well, I don't know, but we can use our K equation to find out. So let's plug them all in. 5 times 5 over 4 times 7. So 25 divided by 28 equals 0.893-ish. Are we at equilibrium? Nope, we are not, because the whatever we plugged in, our positions that we plugged in to our law of mass action do not match what our ratio should be at equilibrium. So in which direction should the system move to reach equilibrium? All right, that's our next concept that we're going to talk about. And we'll actually pick that up next time. Okay, so let me know what questions you have. We'll practice this together. I will see you in class.